Hyderabad and the connectivity problems will not be there. I just want to start the class whenever the students are ready.
You can start, Vishwanath.
Okay. So, can you guys see my desktop? Starting my first class on finite element methods. As you can all see that this is one of the important course for the design stream, both in the civil as well as mechanical sciences. So, and to introduce myself, Dr. Vishwanath Chintapenta. I work at IIT Hyderabad as an assistant professor, and my main area of research is the computational solid mechanics. The core part of computational solid mechanics is to use finite element methods. So I use day in, day out finite element methods to solve problems related to material mechanics, solid mechanics, and others. So this is the natural course that I'm generally teaching at IIT Hyderabad for last couple of years, and I also teach advanced AMOS and other things as a part of my teaching curriculum. So with this as a brief description about myself, I would start this course on the finite element methods, which is part of the final year for the BTECs at JNTU Kakinada affiliated college. So today I'll be giving a brief outline of the course. I'll not be taking much, but I'll tell you what and how I'll be dealing this course in the uh, due course of this lectures. So to start with, the objectives of the courses are to learn basic principles of the finite element analysis procedures. So even before you start learning the finite element procedures, one has to learn about the equilibrium equations, the governing differential equations that carry through. So that I'll be telling you in the subsequent things. And the next thing is to learn theory and the characteristics of the finite element that represents engineering structures. So we know that any given structure is subjected to loads and deformations. So we have to use some techniques to solve this engineering structures so that it can help us in designing those structures. So that is the reason the finite element you will come to know in the due course of the time that it is quite essential for a solid mechanician. And the part of this course objective is to learn and apply the finite element solutions to structural, thermal, dynamic, and to develop the knowledge and skills needed to effectively evaluate finite element analysis performed by others. So this is what happens when you are working in the designing of the structures. You may get several different problems. Some may be structurally loaded, some may be thermally loaded. Sometimes you deal with the transient loading conditions. The structural and thermal problems are further divided into two classes. One is static cases, and the other thing is dynamic cases. In the static cases, we assume that there are no inertial forces. That means mass into acceleration is not there. While in dynamic problems, this mass into acceleration, which is also called as inertial force, that exists into the picture. So the problems which doesn't have inertial problems has to be dealt separately, and the problems which has inertial forces has to be done separately. So that is what we also try to learn both the things in this part of the course. And sometimes what happens when you are working in a company as an engineer, not all the analysis are performed by you. Some of the analysis are performed by the others. You have to analyze and understand the results of the others, and you have to proceed with yours. So we'll also learn how to analyze the results, finite element results performed by the others, and how to apply it for your cases. And finally, we'll try to model the complex geometry problems and solution techniques. This line is pretty simple, but it has very in-depth significance to it. In academic problems, we always deal with a cantilever or simply supported or a slab or whatever it is, very regular geometric shapes. Whereas in real scenario, your geometry is complicated. It can be of any shape. Further, the loading can also be non-linear in nature. So the real world problems are always very complicated, and the analytical solutions what you use generally are insufficient to handle such programs, to solve such problems. This is the place where finite element methods will help you to solve this complex geometries. Let's say any governing differential equation is nothing but either an ordinary differential equation if it is one variable, or it is a partial differential equation if it is two-dimensional in nature. So if you are having a regular geometry, you can put some kind of variable subgroup method or some kind of analytical solutions to get through it. However, if you take a crankshaft or a gear or something like that, these are not simple geometries. They are very complicated geometries. You cannot get the solution of the partial differential equation directly using analytical methods. This is the place, even though you know the theory, your hands are tied and you cannot solve the problems. And to deal with such scenarios, finite element methods will come to your rescue. So finite element method is like a magic tool or a magic wand. If you know this, you can attempt even a complex geometry solution. That is why this has been very important not only for the industrial usage but also for the research. So most of the uh, mechanical engineers who go into industry would require a finite element method because it helps to solve real world problems which are complex in nature. So our course objective for this uh, class is first to start with basic theory behind the finite element method, and then eventually build up to the level where you can handle the real world scenarios. So with this as a course objective, this class has been decided, and I will try to stick to this as far as possible to justify it. Okay, so now knowing the course objectives in detail, now I would go in detail the course syllabus that will be there for this given class. If you have any questions at this point of time, anybody can raise it so that we can discuss over it. Are there any questions? Hello? The course syllabus that will be presented in this class. Shall I proceed? Yes? Okay. So since no one is asking questions, and I too don't know if people are asking the questions, so let me go forward. So this class or this course consists of 6 chapters, and I'll walk you through each and every chapter and how I will be covering it by reading through the course syllabus. So in the next class, I will show some fancy real world problems, how they have been solved using finite element methods and how it has been useful to the industry. That is what I'll cover in the introduction to the finite element methods. Even before we go further down into finite element methods, we need to understand why we are using finite element methods. See, we know that any given structure has to be at equilibrium. That is our main rationale. That is what Newtonian mechanics says, even for the uh, kind of classical mechanics. The same thing when it is applied to the continuum, the same laws of mechanics hold true. Equilibrium equation, even though I'm just telling it briefly at this point of time, this course has a lot of equations that I need to use and I need to write, which I'll be start using it from the subsequent classes. So this class, I just want to keep it simple without no equations. So without any equations. So I'll try to explain equilibrium and other things without uh, usage of any mathematical form. So as we know that as we are even standing or sitting, whatever it is, we are at equilibrium. We are at mechanical equilibrium. The mechanical equilibrium says that you might have studied in your statics or in the first year or second year that total sum of the forces acting on a given object has to be equal to zero. Okay, is what is called Newton's first law, which says that linear momentum balance. The rate of change of uh, momentum is equals to inertial forces. But that is that here, when you don't have inertial forces, it is called equilibrium. When you have inertial forces, then it is called equation of motion. So I will talk about both equilibrium condition as well as equation of motion in the subsequent classes. Now, when you see the difference between a classical mechanics and a continuum mechanics, in classical mechanics, you might have studied in your first year, each object is considered as a point mass or a point particle. However, now we are analyzing, let's say, a piece of a bar or a beam or something. Now, each and every point, we want to see how the equilibrium is satisfied. So that's the reason we need to come up with a metric which can measure the states at each and every point of continuum. So that's the reason one has to introduce something called as stress. Stress, as you all know, is defined as force per unit area in an average sense. Now, we'll have a thorough discussion about the stress in a later slide. Similarly, there is something called as strain. Strain is the actual, it is rate of change of displacement. So when things displace, we will see how relatively one has displaced with respect to other. So that is how the strain definition would come. Now, I will walk you through how the strain and displacements are related to each other. That means given the displacements like this here, how you have to calculate the strain. That's fine. Now, in general, if you are a designer, you'll always deal with the stresses. Let's say you have two bars. One is made up of copper and other is made up of mild steel. Now, both these bars at one end, if you have displaced it by a delta amount by displacement, which is of equal length, then you see the displacement is same, hence the strain is same. However, the stresses in the copper bar is different from the stresses in the mild steel bar. Do you know the difference? The difference is each one has different modulus. See, modulus is like its material characteristics. I would go a little bit aside and I will tell you that when some professor or somebody delivers a class, the same amount of thing has been delivered to all the students. However, some people come class first, some people come at an average, some people will try to barely pass through the course and some will unfortunately fail the course. its strain and displacement are like the amount of things the professor or a lecturer has delivered to you. However, your performance is not proportional to, is not same for each and every individual, because it is depending upon your own behavior. Like that, every material has its own material behavior. That material behavior is natural to it. So one guy may be very good at mathematics, one guy may be good at physics, one guy may be good at cricket. So one say that he is natural at playing sports. Like that, every material has its natural tendency to respond to the strain. And that tendency is measured using a stress strain relationship, or also known as constitutive law. So that we'll be teaching in the first part. Further, you need to know that in most of the strength of material courses you have done, you have studied the bars and beams and other things as 1D. Now we'll also, maybe in the AMOS courses, you have started studying in the 2D and 3D. It is natural to study the structure in the three-dimensional space in its full form. But what happens is, it is very complicated to study a structure in its three-dimensional state. If you look at us, everyone is three-dimensional in nature. Even if you look at a bar or a beam that is running over your head on the below the floor, on the ceiling, you would see that when you are modeling in the class, you would model it as a one-dimensional bar or a beam according to the type of loading. So similarly, if you want to relax a little bit, so people try to study it in two-dimensional state, not totally three-dimensional, because three-dimensional will be much more costlier. So there are some natural reduction to the three-dimensional state to the two-dimensional state, and those states are called plane stress and plane strain conditions. So we will see that what is a generally, as a rule of thumb, if there are any structures just like of the thickness of a paper or of that order, that is, thickness is very small, in those cases you consider it as plane stress condition. Whereas if you are analyzing a cross section of a dam where the dam runs over a half a kilometer or several hundreds of meters, then each cross section is constrained by a lot of material in the either side. The thickness is very huge. In those conditions, it is called plane strain conditions. So we will also see that how you can break up your three-dimensional structure to your two-dimensional structure so that you can solve the problems with less complexity. Studying a problem with three-dimensional makes lot of computational cost, as well as analytically it is also difficult. Okay, so that is what you will cover in the first part of the unit 1. Now what you are doing is you're studying the equilibrium equation. This equilibrium equation is nothing but uh, a partial differential equation. A partial differential equation, as you might have studied in your math 1 and math 2 or 3, whatever it is very difficult to solve. One can also say that sometimes you never know, for a partial differential equation for a given boundary condition, the solution exists or not. So let me digress and give you one simple example. Let's say if I want to have a joy of driving my own car, let's say I want to buy a Baleno. Now it would cost 9 lakhs. Now in my pocket I don't have 9 lakhs. Maybe I'm a poor fellow. So now what should I do? Just sit quiet and should not live my dream? No, right? I would go approach a bank and I will say that I want a loan. I can pay EMI maybe monthly some amount, and I can start driving the car by tomorrow because I'm purchasing on a loan. So finite element is also very is similar in nature. Because if you want to solve a partial differential equation in analytical sense, you need to have full down payment. But in finite element methods, it is like buying through EMI. You don't have stringent conditions. It's like if I have 9 lakhs only, I can drive the car. But in finite element, I don't need to have a 9 lakhs. Even if I have 1 lakh, I will put something, and then every month I'll pay some amount to get the loan cleared. So finite element can also be considered in the same sense. So that means your analytical problem is different from finite element problem. Both the problems are not same. One does full payment at one time, one pays partially by through chunks and pieces. That's what similar to finite means, but the finite has a different meaning also at some other point, we'll tell you. Now, there is another example which I think you may like it. I'll try to tell you at this point of time. So let's say if I say that in this course, if you have to pass, you have to secure 50, 50 out of 100. It's a stringent condition. Not everybody would get 50, right? Maybe because you fell sick or you have to watch a World Cup match. So you missed a couple of lectures and you didn't get anything. You get 40, 45, 35, you would fail the course. Now, this is what an analytical or partial differential equation says, that each and every student has to attain 50 to pass the course. Now, instead of that, I would say that I'll group each one of you into teams of 4. And as a team, if you can score 50, then I would pass you. Now that's a very good proposition, right? Because if there is a topper in your batch, he would score 100 out of 100. You can sit, watch your World Cup match, you don't score anything, still you would pass. Yes or not? I hope so. Because I'm not getting a feedback, I would continue. So finite element is also the same thing. So instead of reducing the error at each and every point, we group people, we group nodes or group it as an element. Over that, we'd reduce the residual to 0. So that is what is called traditional finite element methods are developed in this nature. As a group, if you minimize the error or reduce the error by multiplying by weights, then it is called weighted residual methods. That we'll be covering it. So when you write this weighted residual method, you'll end up with a different form of equilibrium equation. And that equilibrium equation is also called as weak form. So the difference between a strong form and a weak form is strong form requires full down payment to get the car. Weak form doesn't require full down payment for getting a car. I can still get you the solution, like buying a car. So one can show that this equilibrium equation which you have studied in your AMOS or mechanics of solids or solid mechanics is a strong form, like a strong coffee. It's a strong form. You need to be having all the criteria given to get the solution. Whereas finite element is like a magician. It's like a magic tool. It says that you don't need to have full thing, but still I'll get you your solution. That's the reason this finite element has been very popular, because it promises solution in spite of having a complex geometries, or you don't know how the things would evolve with time, or non-linearities. So one can show once you write your equilibrium equation from the strong form to the weak form, then you are ready to start working in the finite element sense. So one can show that the variational methods or weighted residual methods would eventually lead to writing your equilibrium equation in terms of energy. And that principle of virtual work is also the same as the weak form or residual form or variation form, all these forms are similar. Now with this, since it has been so much overloaded, what we'll do is, to make you understand these concepts, we will take one-dimensional problems to help you to understand these things, the difference between a strong form and a weak form, with 1D problems like a bar and beam into the things. So this is the part unit 1, which we'll be covering in detail. I'll go through it with lot of equations in the subsequent classes. But now I just want to give a bird's view or just an outline of the chapters. So now at this point of time, if you have any questions, please feel free to stop me and then shoot some questions at me. Now, since you have a complicated or a complex geometry, you, as I said earlier, we want to break entire class into a team of 4 or 3, like you do for your projects. Like that, my entire geometry is divided into small domains, and those domains are called elements. And these elements can be of different shapes. For 1D, they are linear in nature, but if it is 2D, it can be triangular, it can be quadrilateral, that is trapezoidal, square, rectangular, and other kind of stuff. Or for 3-dimensional, it is brick elements, that is solid elements. So how the domain discretization has to be done? Now let me again give you a parallel analogy about how to buy that Boleno car of me. Can I get hold of my car maybe in next 100 years? Never. Maybe. Even my son and grandson has to keep on paying the loan, right? Or can I put entire my salary into the things? No. Maybe 20% of my salary I can afford to pay as an EMI. I'm just giving a guess because I need to feed my kids and my family, right? So it's the same thing. So when you're discretizing your complex geometry into subdomains or domains, what is the natural part of discretizing it? And if I give more refinement, then I have to wait forever to get the solution, right? Or if I do very crude with one element I'm trying to do, I may not get that solution I'm promising. So anyway, at this point of time, I need to stop and tell why I'm telling like this. Yes, finite element is a magical tool, but you need to understand that if you solve analytically, you'll get exact solution. But if you solve through finite element methods, you get an approximate solution. Now, solution is approximate. That is the key point in the finite element solution. Finite element solution, I don't promise that it is always exact. Under certain conditions, it will get as close as possible to the exact solution. So if somebody gives a finite element solution, don't believe him blindly that it is correct. First, you need to walk through the assumptions they have made and the discretization they have done, how the loading has been applied, and several different things. And then you justify for yourself, does that result make sense? So that's the reason I want to again reiterate that finite element method gives you solution, but it is not exact, not necessarily always. It is an approximation. But what do you want? I Anybody is to bring the disparity or the difference between the exact solution and the approximate solution as low as possible. That is our aim. But if I already know the analytical solution, why I would even go and work on the finite element solution for a complex geometry? So that means we don't know we always that how our solution looks like, but still we are targeting for our solution. That's a good part of it. But there are certain thumb rules that will help you to attain this closeness to the exact solution. If you stick to that, you'll get your solution. That all the things you will learn during the due course of this classes. So So let's come back to the discretization. The discretization of the given geometry has to be discretized into domains of different shapes depending upon 1D, 2D, and etc. And there are certain procedures to it, how to discretize it. Now, when you discretize it, what you're doing is you will be writing your equilibrium equations. Now, your equilibrium equations has been already studied in the chapter 1, but that equilibrium equation is a continuous equilibrium equation. At the second part of the chapter 1, you have studied the equilibrium equation of the continuum, not in the strong form, but in the weak form. Now, what you're doing in the finite element is you are still writing the equilibrium equation, which is the governing differential equation, but in a discrete sense. So it's like saying welcome, namaste, or bagunnara, whatever it is, in different languages. But the meaning of it is that you are welcoming somebody, right? Similarly, you're writing equilibrium, but we cannot solve the equilibrium equation in strong form. Weak form is like an intermediate form, unless you write that you cannot go into discretized equilibrium. So you write your discretized equilibrium for individual elements. But I'm not worried about each and every individual equilibrium. I'm worried about the entire structure equilibrium. So to get the entire structure equilibrium, we have to take the stiffness matrix of the each and element and have to assemble to the global stiffness matrix to represent the structure stiffness matrix. There are certain protocols for that I'll be walking through in the due course of the unit 2, and there are several storage schemes. Most of the time what happens is our equilibrium equations, let me just stop and I retell the things. So the discretized form of equilibrium is nothing but Ax is equals to B form. That is, A is a matrix, X is an unknown, B is the forcing vector. It is also known as K U is equals to F. Don't worry about the equations. I will tell you equations in the subsequent classes. Here I just want to give an overall view. So we will be writing a lot of equations in the subsequent classes. So don't worry that if I'm not writing an equation today, it is not a grave danger, but we'll come back to those things in the coming classes. So anyway, Ax is equals to B in a finite element sense is nothing but Ku is equals to F, where K is a stiffness matrix, U is unknown degrees of freedom for which you are solving, F is the forcing vector where forces are acting on the structure. So this K is a element stiffness matrix you'll be assembling into the global stiffness matrix. It so happens that even in your class, let's say in your given class, you talk to your next two neighbors, maybe four neighbors, very closely. Do you always talk to the last bench fellow? Or the last bench fellow, does he talk to another last bench fellow always? No, you are only close to the next near people. That means your connectivity is only bounded to maybe two, maybe four, or at most maybe six or 10. You may have 10 good friends, but in a class of 60, I don't think so. You are connected to all the 60 people. The same thing, your domains are also not strongly connected to all the elements. They are only connected to the neighboring things. Because of that, in the stiffness matrix, you will end up with a lot of zeros. Now, when you are solving this finite element method, you have the matrix, which is not 3 cross 3. It can be 10,000 by 10,000 or 1 million by 1 million. In these kind of things, you will have only very specific entries which are non-zero, and the rest of the entries mostly zero. Mostly zeros, you'll end up taking up all your memory for storing insignificant values. Let's say there is a function at your home and your dad says that book a hotel room for every guest he has sent an invitation card. Is it a feasible thing? You know that some guests would not end up to the event. So you will only book rooms to the guests who were there on that given event day. Otherwise, you have to pay a huge bill, right? The same thing is in the finite element methods. If you end up storing zeros in your memory, you end up paying or occupying a lot of memory in your storage. And because of this, your code becomes slower. So in order to deal with it, there are special storage schemes like banded storage, skyline storage, and other different kind of things, which will be dealing for a banded storage. You need to know what is the bandwidth, and only the the data within the bandwidth are mostly significant, and outside are completely insignificant. So you will not even get to store such zero values. And in order to reduce the bandwidth, you need to number them appropriately. So we will see what is the best way to do node numbering, how to generate the mesh, and other kind of things. So that is the most first part of the unit 2. In the subsequent part of the unit 2, you'll be talking about interpolation functions. See, the finite element methods has its roots in linear algebra. Okay. In the linear algebra, the first part mostly people will study is polynomials and polynomial interpolation. So for suppose if you know the value at two different positions, if you want to get a value somewhere in between, the natural thing one would do is interpolate it. The same thing is used in the finite element. What you do is, once you know the nodal values, for a nodal values means if you know the displacement at the certain nodes, you would try to get the nodal value, try to get the displacement value in the intermediate position between the nodes using some functions, and those functions are called interpolation functions or shape functions, are also known as Lagrangian functions. These are called Lagrangian functions if it has single degree of freedom. In the subsequent chapter, we will also go through Hermite functions. Let me not jump over it. So those things, how to develop it. And sometimes it is good to write it in local coordinate system, sometimes write to global coordinate system. Why all these things are required, I'll tell you things. And the next thing is convergence requirement. See, you're assuming an approximation. Okay, it's like gambling. You'll think that the next third ODA between West Indies, India will win. I don't know, I generally don't bet, but I'm giving a very bad example. And you go and bet, right? But there should be some basis for you to do such kind of things. Maybe you have seen the second match they have won in so huge margin, and everybody is in good form, so you will go and bet on them. For suppose they didn't do well, would you still bet on the same team X? No, right? The same thing. Like that, there are certain requirements, convergent requirements one has to meet for the given approximation you have made. Okay, so those things will be carefully described. If the convergence requirements are not met, the problem would be if you double the mesh, that means if you refine the mesh, you would be expecting that your solution will converge. Sometimes it would not converge, it would not give any different change, which is a serious issue. If you are increasing your manpower, your solution should of time. I want to again say what is a finite element. If you take a analytical solution, if you take a bar, analytical says the solution says that, or analytical form of the partial differential or ODE says that if you take any small infinite seminal element, the equilibrium condition is to be satisfied on it. Now, in finite element, what you're saying is the size of the element is not infinite seminal, it is of finite size. Okay, so that is the crux. So that means In the finite element methods, if I take a bar, I can solve it as one element solution. I can cut it into two elements, I can solve two element solution. I can cut it into four, I can solve 4, 8, 16, 32, 64, so on, so on. I can even make infinite elements of chunks. So that means if I make infinite elements, your finite element should become an analytical solution. That is the other thing. So, but we know that in order to get a simple solution of a bar or a beam, you are using infinite element. That means you are going to spend, if I give us a problem to now to the computer, it gives me after 1 year, it is no use. By that time, the product would be released by my rival and they will make profits. So that means we need to understand what is the real amount of refinement we require. If you want to know what is the real amount of refinement you require, you need to know that if I double the mesh, how soon I would converge the exact solution. So there are certain things, the conversion requirements has to be met, which we'll go through in detail, and how to deal with the boundary conditions that also be dealt with the unit 2 of the course. At this point of time, again, I will break and I will ask if there are any questions from the audience side. Hello. If there are no questions from the audience, I would again go ahead and real problems. As you have seen in your statics, there you have studied a truss problem. Here also you are studying the truss problem. The difference between the truss problem at that place and this one is, there you are assuming when you are studying in the statics that each truss member is rigid and it is only transmitting the force. Whereas in the AMOS, when you have studied the truss, the same thing you will be studying in the finite element methods by modeling each of the member of the truss as a one-dimensional element, and the entire truss is assembled to the global stiffness matrix, apply the loadings, apply the appropriate boundary conditions, and get the forces in the each and individual member of the truss, as well as obtain the reaction forces and the displacement of each and individual member inside the truss. That is the first part of the unit 3. Unit 3 is nothing but a natural extension of the one-dimensional problems that you have been learning in the unit 2, but it's a two-dimensional problem using the one-dimensional beam structure to construct a two-dimensional structure. So it is nothing different from unit 2 problem, but it is a higher manifestation, and it will help you to solve a real good problems like a uh, the cell phone tower or some antennas and other kind of things. So the second part of the unit 3 consists of analysis of beams. Now at this point of time, I would like to just talk a couple of minutes about the beam. As you know that the difference between a beam and bar is, a bar is a unidirectional member, with that means your length is most significant compared to your cross section, and the load is applied in the longitudinal direction. However, in the beams, the beam is also significantly in one dimensional more, your cross section is less, but on the beam the load is applied in the transverse direction. Don't worry about the pictures, I'll come back to these things at a later point of time. Now for a beam, for a bar, at each and every node, only the axial displacement is the unknown degree of freedom. However, for a beam, you know that not only here, since the load is applied in the transverse direction, your displacement is also in the transverse direction. So the displacement in the transverse direction, and each, so W and dW by dx both are degrees of freedom. So unlike bars, the beam has 2 degrees of freedom per node, and hence your Lagrangian interpolation functions are not valid, because Lagrangian interpolation functions are derived based on 1 degree of freedom per node. However, this is 2 interdependent degrees of freedom, that is W and dW by dx. For such kind of things, one has to develop Hermite interpolation functions. So once the Hermite interpolation functions are there, then using strain displacement relationship, the strain is obtained, and then the stresses are obtained, and then stiffness matrix are obtained, and the element stiffness matrix for the Hermite beam is obtained. And then how to deal with the uniformly distributed loads, simply supported beams, and other things will be analyzed by using assembly and other kind of things. And then you will be solving a complete beam problem in the second part of the unit 3. So this is the place, this is the core of the finite element where you will be spending most of the time. So even my lectures has been heavily weighted, because this is the place one can clearly understand the formulation of finite element, and once you obtain the solution, how it is, how you can understand the problem and how it can be applied. Everything is will be more apparent in the second and third chapters. And the third chapter is the place where I'd be spending most of the time, and you will beautifully understand it, because bars and beams and trusses you might have solved it analytically in your other part of the courses like statics, mechanics of solids, and other courses. Now, with this would be the end of the one-dimensional problems, truly, for the things. So at this point of time, one can say that I know mostly about the finite element. So at this place, again, I will stop, and then I'll ask for some questions from your side. Hello? End of unit 3, which would be close to your mid-semester. Your one class will be after your mid-sem, the first mid-sem, I guess. So now, by the mid-sem, you would clearly understand what is a finite element. But you know that no structure is truly one-dimensional. You are making an approximation that it is a one-dimensional in nature. So in reality, the structures are three-dimensional, but a closest approximation one can make is you can ignore the thickness direction, or using plane stress or plane strain condition, you can reduce them to two-dimensional structures. So then the question arises, the things what you have learned in a one-dimensional sense, can it be applied to solve the structures in the two-dimensional way? Most of it, 80% of what you have learned in the one-dimensional sense will truly apply to the two-dimensional things. However, with the increase in the dimension, there are unknown complexities that arises. That things are like not only convergence issues because of two dimension, but also compatibility issues will come into the picture. So we will also deal with these kind of problems in the two-dimensional framework, how to obtain your 2D formulations using constant strain triangles, linear strain triangles, quads, and other things, how to treat your boundary condition and solve a nice plane stress or a plane strain problem, is what you'll be covering in the first part of the unit 4. The next part is the axisymmetric problem. Now, I think you might have done CAD CAM in your courses. If you want to generate a hollow cylinder, how would you generate it? You take a rectangular strip about an axis, you sweep it 360 degrees to get a hollow cylinder, because your cross section at any given point is symmetric about an axis. The same symmetry, if you, can we use it in our finite element formulation, is the question. Yes. we can use it. Now, why we have to use it? If we don't use this symmetry condition, the problem is to solve a three-dimensional structure. You know that the cylinder is loaded axisymmetrically, the geometry is also axisymmetric. Then why you want to solve a problem in a higher sense when you can solve it simply? How you can solve simply? If you know how to deal with axisymmetry formulation. So this is what you will be learning in the axisymmetric formulation, and you will be solving a thin and thick cylinder possibly with a pressure loading or some axisymmetric loading, and the formulation of it will be dealt in the unit 4. So with this, you are ready to think about two dimension and higher. Once you know the two dimension, in real world, even in the industry, mostly you will be solving three-dimensional problem. The extension from 1D to 2D is a giant leap. However, the leap from the 2D to 3D is not a giant leap. Everything is same. Even in 2D to 3D, things are same, only one more added variable. However, the leap between the 1D to 2D, the unknown features will be coming. That still remains same when you jump from the 2D to 3D. So that's the reason three-dimensional finite element modeling is not dealt separately. It is assumed that once you know the two-dimensional state of stress, three-dimensional or higher dimensions are more or less same in nature. So at this point, unit 4, you are well versed not only with one-dimensional problem as well as two-dimensional problems. Since you guys are not posing a lot of questions, I would go ahead with the next chapter. So in the third chapter, fifth chapter, um, I'll be dealing with the higher order elements and isoparametric elements. See, what is the necessary of higher order elements you'll come to know if you only understand the convergence criteria, which I'll be telling in the second and third chapters anyway. So you know that sometimes like your constant strain triangles are not enough because they interpolate the things in a linear fashion. That means your strain would be constant. Sometimes you know that you want a faster convergence. It's like if you have um, a bike, you go to your dad, you ask for a bike, he will say, why don't you take a Passion Pro or a Glamour? You would say, no, I don't want that. I want KTM or a Duke or whatever it is. Just like that, because it has a higher speed, has a passion factor, and the ride is so good, and other features are there. Similarly, you can reach to your destination much quickly, or you can showcase about your driving skills to your friends and whatnot, anyone. The same thing, sometimes we also require our solution to be reaching faster. And if you take a bike like a smaller, slow moving vehicle, Glamour or a Passion Pro, it is no good. So we have to go for KTM. KTM means it is costlier. So same thing, higher order element is like KTM, whereas linear order elements or lower order elements are like a Passion Pro or a Glamour in nature. Now, those formulations are only little bit different, and how to formulate those things we'll be talking about it. And there is something like compatibility issues. I think compatibility issues are very difficult to tell. I don't know if I can take this very bad example. It's like compatibility between husband and wife, maybe a compatibility issue between two neighbors, or a compatibility issue between a girlfriend and a boyfriend in nature, right? The same thing also, there is compatibility between two elements. They don't speak same. So let's say between two neighbors, if they don't agree between the boundary wall, they say that you have encroached into my land, I have encroached into your land, something like disputes are there, then there will be unrest. There will be always fight. That means the neighborhood will be in huge disturbance. The same thing, if between two neighboring elements, they don't agree on the continuity in the common boundary, that will lead to compatibility issues. Now, if you do normal formulation, your compatibility issues are prevalent. But fortunately, if you go and do it in an isoparametric element in natural coordinate system, you will see that such kind of issues are not there. That we'll discuss in the later part when we do it. However, if it's a one-dimensional structure, these kind of things are not there because at one-dimensional, the boundary is only node. At node, no matter you're estimating from one element or the other element, it is exact, it will satisfy. So only in the two-dimensional and higher dimension compatibility issues are important, and isoparametric is one way to rescue us from such certain scenarios. And that's the reason you also formulated an isoparametric and natural coordinate system. Natural coordinate system is like a template system so that you don't have to do that work again and again. You'll use a template, right? If you want to write a leave letter, no, nowadays nobody writes a leave letter in a white paper. They take a standard template. You'll say, I'm not coming from so and so date to so and so date because I'm unwell or I'm going to friend's wedding or something like that. You use a template like that. Natural coordinate system will offer you template because when you are running for millions of elements, you need a template. You will not do it the same mundane task again and again. And at this point of time, I want to stop and say one thing about finite element. People who do finite element are generally miser, or also I don't know what you call conjus Marvadi. I don't know if there are somebody, if I'm offending somebody, don't take it seriously. So Kanjus are like they're spendthrift. They don't spend more. Okay. So it's like, let's suppose my dad is spendthrift. I go and ask him, I want to take my girlfriend to a picture, give me 200 rupees. He would put 50 rupees and say that is more than enough. Right? That kind of thing is there. The same thing because he's a spendthrift. Let's say, generally my dad is never like that. He would give me 2000. But for an example sake, I would have given you that. So let's come back to the point. Finite element is also like that. In finite element, you do huge number of calculations on huge number of elements. So on each and every element, if your calculations are more, you'll end up spending more amount of time in the computing. Nobody wants how much wait time. Answer. But paper computing, maybe now you are going to get it. Still, you need to reduce your computations. To reduce your computations, you need to be spendthrift. You need to be seeing that how I can cut the cost. The same thing. It's like if my dad is there, he would say that uh, near to next door, the shop he would sell in 100 rupees. If I go 1 kilometer down, he would sell in 20 rupees. He would make me walk 1 kilometer and get the stuff. The same thing, if the product you are getting is same at a lesser cost, then we would always prefer the lesser cost solution. So that is what natural coordinates will help us to give a template form. Once the template form is obtained, then we are ready to use it again and again, and it will reduce our computations. That is one part of it. And the last part of unit 5 is numerical integration. So I always say that even from my childhood, I have seen several professors telling me that computers are dumb. We are the only intelligent people. I think that is right. The computer does what we ask. It doesn't have the brain of its own. We write a program, it will give it. But in fact, what are computers? Computers are nothing but transistors. They open the gate, they close the gate. So if they open the gate, close the gate, then they can do addition and subtraction very well. But they cannot do integration. Now we are talking about numerical integration. Now, what is integration? The integration is nothing but if you take a domain and cut it into infinitesimal small rectangles and add all those rectangles, infinitesimal rectangles, you'll get the area under the curve. So instead of infinitesimal rectangle, you make it finite rectangle. That will automatically become trapezoidal rule, Simpson rule, Rangakutta, whatever it is, whatever you want, it will come. So, but again, I've told you that finite element guy, whoever does finite element is a spendthrift. Spendthrift means with lesser, so it's like Indian nature. Um, Dil mange more, right? So for less amount, you want more stuff. So that's what when you integrate a given curve with n points, you'll get accuracy up to n minus 1. But we don't get satisfied with that. We need more. We want more and more. So Gauss has said that if you use Gauss kind of integration with up to n, you'll get 2n minus 1 polynomial integrated exactly. So we'll also see this kind of integration. And why we have to worry about the integration? Because our stiffness matrix is formulated as integral B transpose dB. Don't worry about the equation. I will tell you this thing again at a later point of time. So the stiffness matrix at an element level is obtained by integration of some strain displacement matrix multiplied by consecutive response multiplied by strain displacement matrix over the given domain. So this integration computers cannot perform analytically. It has to perform numerically. Even we also know it in numerical sense. So we also have to know how best we can integrate it with less effort. Everywhere we are like a spendthrift. In the finite element formulation, whoever does finite element formulation, you will see that with minimum I can achieve more. It's like with less I need to achieve more. So with this, it will completely give you a full perspective of finite element formulation at the end of Unit 5. Now, the last chapter of this course is Unit 6, where we'll be studying about, up to this point of time, we are mostly dealing with the uh, structural problems and also static problems. Static means inertial problems are not there in the picture. In the Unit 6, first part of it, we'll be talking about non-structural problems like heat transfer problems in two-dimensional things using a problem of using analysis of a fin or a thin plate in 1D and 2D respectively, and also we may also study structural problems like uniform shaft subjected to torsion and other problems. This is the first part of the sixth chapter. At the second part, what we'll be doing is dynamic analysis. In the dynamic analysis, we have inertial forces. Instead of equilibrium equation, since F is equals to 0 is a equilibrium equation. F is summation of F equals to 0. Whereas summation of F is equals to mass times acceleration is equation of motion. So equation of motion is solved in the dynamic analysis. It is little bit different from the static analysis because in here, once the mass is there, you need to write mass matrix. So mass is approximated as a lumped mass matrix, and you will also have to find out the eigenvalues for the free and force vibration and other things, which we'll be solving in the Unit 6 in this part of time. So this constitutes the syllabus of this course and how I'll be dealing it in the coming classes one after the other. So these 6 chapters completes the syllabus of this given course. So at this point of time, if you have any questions, I would again stop here and I would request you to these two. I think you would be having your course curriculum, course syllabus. So I would ask you to go through it and if required, subscribe it in your library, and or if you want to purchase on your own, I would request purchase one of the things because this is mostly covers what I'll be dealing with it. And there are a lot of reference textbooks. Okay, the reference textbook consists of these following, which is like finite element methods with applications in engineering by Desai, Aldao, Shah, Pearson Publishers, and Introduction to Finite Element Methods by J.N. Reddy. He's a one very popular guy, and I think this book is quite popular in India. Then Finite Element Methods for Engineers, Kenneth Huber, Donald Deveris, Douglas Smith, and Byrom, John Wiley and Sons, Private Limited. So this book is also a thing. The fourth one is Finite Element Analysis, Theory and Applications with ANSYS, Syed Movni with Pearson Education. But out of all these things, I would recommend the fifth book. This is my personal choice and I have added it. This is Concepts and Application of Finite Element Methods by Robert Cook, David Malkus, Michael Pesha, Robert Witt. There is Willy student publication edition, and it would cost around like 500 rupees. This is a standard book where I would generally suggest for BTech as well as MTech people that are required. And over the years, several faculty have also recommended these things. So even other books are advisable, but uh, I would love the fifth book. This is my personal choice. So there are even advanced books like Zinkovic, Bathe, and um, other books by other authors, Hughes and other things. But this would be suffice for the for BTech curriculum. So 1 through 5 reference books. If you have any library, you can go and try to browse through it at your will. And however, I would re-emphasize that if you want to buy certain textbooks, these two textbooks are a good thing for a start. Again, I would reiterate Introduction to Finite Element in Engineering by Chandraputla, Ashok and Belagundu, print as Hall Publications, and the Finite Element Methods in Engineer by S.S. Rao, Pergamon Publications would be a best bet to buy. And these 5 books are the best ones to kind of have it as a reference textbooks. Now, you have tried to, I think now you have gone through the course outline in greater details. So you have started with certain objectives, and at the end of this course, there should be some outcomes, and the outcomes would be the following. So I'll walk you through it. First thing is to understand the equilibrium equations, and then understand the concept behind the variational methods weighted residual so that you can write the weak form for the finite element. This is the first outcome that you will be learning if you rigorously go through this course. The second thing is to identify the application and characteristics of finite elements such as bars, beams, plane, that means plane stress, plane strain, axisymmetric elements, both normal elements as well as isoparametric elements. If possible, we'll do 3D elements. 2D, as I said earlier, 2D to 3D is a natural extension. It doesn't need much things to be dealt with. It's more or less same. The third one is develop element characteristic equation procedure and generation of global stiffness equation. So how to obtain the local equilibrium at the each and individual element, and how to obtain the global equilibrium by assembling the global stiffness matrix is what you will be learning. And then apply the suitable boundary conditions to the global structure and reduce it in the solvable form, and then invert your global stiffness matrix to solve the unknown degrees of freedom. Once you know the unknown degrees of freedom, again you put it back in your uh, interpolation functions and try to obtain your solution all on your boundary, all on your domain. Okay. So next, the final thing is to identify how the finite element method expands beyond the structural problems like thermal problems, not only static problems, but also equilibrium problems, heat transfer, fluid flow, and other things. So with this as an overview, I would like to say a few things about the finite element. Again, I might have told you once that finite element is like a magic tool. Even though you cannot solve for an analytical solution, you can get an approximate solution. So this is it's like a hot selling cake. Just because it's like somebody doesn't have a solution and you're promising at least an approximate solution. That's the reason the finite element is very good, and everybody in the mechanical sciences should learn, because all physical phenomena in this universe is governed by partial differential equations. So what you are converting in this finite element course is converting your partial differential equation into weak form, In the weak form, you are putting the numerical approximation and converting into a set of linear algebraic equations which replicates the same equilibrium equation that is there in the analytical form. And once it is in the linear equilibrium system of linear equations, you can invert it and find the solution much easily compared to the PDE form. And once you know the solution at random node, at the assigned nodes, then you can even obtain the solution everywhere inside the domain using the interpolation function. So I'm reiterating this again that this is like a magic. It's only a simple geometry, complex loading, and different kind of multiphysics. Finite element is not only used in solving structural problems, heat transfer problems, fluid problems, but it is also solved in solving multiphysics problems like electromagnetism and other things. Okay, so with this, I would say that please pay attention to this course closely. If you have any questions, you can ask me, or if you cannot ask because of any bandwidth limitations, you can always send it through the coordinator. I will try to answer each and everything to the satisfaction. And I want you to learn this finite element so that it will help you even if you choose a master's program in your later part of your career, or if you go to the industry, this would immensely help you because this course will help you to solve real world problems. And I hope you will have a good course. And at this point of time, I will stop and ask for the question session.